It's a great pleasure for me to introduce our next speaker, Dr. Michael Brown. The story that he's going to tell you is one of the most exciting stories in modern planetary astronomy. Dr. Brown is the discoverer of many of the worlds beyond Pluto, beyond Neptune indeed, and it is his discoveries that have caused a lot of the trouble about Pluto that you've heard so much about in the news media. Dr. Brown is professor of planetary science at the California Institute of Technology in Southern California. Because of his troublemaking work, he was named by Time magazine the year of his most important discovery, one of the 100 most influential people in the world. So we're delighted that he's brought that influence to bear for good rather than evil. He has continued to search the skies for other interesting worlds to make us think about the solar system. So here, to tell you about how I killed Pluto and why it had it coming, also the title of his forthcoming book, I should say, it's a pleasure and privilege to present Dr. Michael Brown.
Thanks. There's still a few holdouts who have survived the weekend and made it to the end here. I only barely made it to the end here. I just flew in from Argentina yesterday, so I'm only barely awake. If I fall over at any point in the talk, and it's not because I trip on this, somebody just wake me up. I'll be right back. So let's see. I'm feeling a little. I tend to wander during my talks, and so I'm feeling a little constrained by all this here. But I'm going to try to keep myself in this little triangle, just like this. So indeed, I'm going to talk today about Pluto and how Pluto was killed. And I know by now most of you are over feeling unhappy about it. Is there anybody who still likes Pluto? Okay, well, if by the end of the talk you're still mad at me, you can find me. I'm at Caltech, and it's right there. So the story of why Pluto had it coming started with the discovery of Pluto itself. In fact, it started even before the discovery of Pluto itself, when astronomers in the early part of the 1900s started looking for this mythical planet X. And I'm sure most of you know the story that this planet X was out there, and it was thought to be out there because it was influencing the orbit of Neptune, tugging along on Neptune. And so astronomers could use all this new fancy physics that they had figured out to learn where planet X was. And so they did calculations to try to figure out exactly where it was, went to the sky, went to the telescope, took a picture looking for planet X, and sure enough, there it is. Yep. Do you guys see it? So if you can't, so I feel bad for you guys right around in here, because I'm going to stand right about here the entire time. So if I'm in your way the entire time, please feel free to get up and move somewhere where I'm not quite so irritated. So it's actually not really right there. This just looks like the sky. And the reason that the astronomers thought they would find planet X by simply looking at a picture of the sky is because they thought it was big. They thought it was the size of Neptune, or larger if it was tugging Neptune along. And if Neptune were on this picture, it'd be sort of this big. It'd be this huge thing in there, and you would know it. You would know it just like those initial discoverers of Neptune. They didn't have to do anything fancy to find it. Once they knew where to look, they looked in the sky, and sure enough, there Neptune was. And on this one, it wasn't the case. Of course, all of you know the story now that by about 1930, Clyde Tombaugh had been hired to come work at Lowell Observatory down in Flagstaff to find this mythical planet X, and he figured out that he was smart enough to know that he didn't know how to find it, how to just know what it was when he looked, and he realized the only way to find planet X was going to be to take a picture of the sky and come back a day later and take another picture of the sky and watch it move. You guys saw it move, right? Okay, let's try again. Here's night 1, night 2. Anybody see it? Yeah. Liars. There we go. Try again. Night 1, night 2. I don't know why, but for some reason the fourth time everybody always gets it, but I can't figure out why. Here's night 1. There's night 2. That is. Here it is without the arrows. These are the actual discovery images in 1930 of Pluto. He only looked 3 times. He didn't do 4. So there it is. That's even Clyde Tombaugh, though, was surprised because, you know, it looks really small. It's so small that, I always forget which one it is. Oh, it's this little one with the tail right there, right? That's it, right?
Yeah.
Okay. So it's so small, it looks just like a star. It doesn't look like anything big and planet-like. And in many ways, I wish I were an astronomer back in 1930 because they got to be a little more crazy than we are today. We're pretty crazy still. But they got to feel less constrained by physics because physics was less old at that time. And so they came up with a lot of theories on why, even though they knew Pluto was big because it was tugging Neptune along, why it looked so small. How could it possibly be so massive even though it looked so small? And there were some semi-wacky ideas, but my favorite wacky idea is one that I read, which was that it actually has a core of solid uranium. So this is 1930, so they didn't realize that that's actually a really bad idea. Core of solid uranium, and then it has a liquid oxygen ocean surrounding that core of solid uranium. So it looks small because you're only seeing that core of uranium, which is actually can be pretty small because it's pretty dense. But actually the liquid oxygen ocean actually functions like a lens too. It makes it look even smaller. So what I don't want you to do is to go home today thinking that maybe Pluto is made out of uranium with the liquid oxygen ocean. It's not actually true. In fact, it's not very massive at all. And these days we actually know a pretty good reason. There's a really good reason why Pluto looks so small. Anybody guess what it is? Oh yeah, it's because it's really small. And it took a long time to figure that out. And this is one of the reasons why, of course, it was a planet back then, is because it was massive. We knew it was massive, even though it wasn't. It's so small that I'm gonna show you this picture a lot of different times. I'm gonna put it on, and this is showing a real picture of the solar system is impossible. You can't both show how far apart planets are and how big they are. You can do one or the other. So as a compromise, most pictures you ever see of the solar system do neither. And they make these horrible pictures, like my daughter has a lunchbox of the planets. And you know, Mercury and Pluto are the same size, and Jupiter's about that much bigger, and the Earth is a little bit between the two. And they're all crammed in together, and there's aliens flying around. And it's these things give you an incredibly bad impression of the solar system, so bad that most people really don't have a very good feel for how big things really are. So I like this one. It doesn't show you the sizes of things, so I've had to cram them all onto one page, but it does okay. Okay, so we have Mercury up the top, Venus, Earth, Mars. I actually have the asteroid belt in the middle here, and these are all, everything is real sizes. You can see Ceres, there's the biggest one there, and these ones that I have shown only things on this slide in the solar system that are big enough to appear as one PowerPoint pixel. That's the criterion for inclusion. And so there are, I think, 10 asteroids that are a PowerPoint pixel size. Jupiter, really big. Saturn without the ring, still big. Uranus, Neptune. If we put Pluto on there, it's really, really, really kind of small. So small that if you're sitting in the back, maybe you don't notice it's that little insignificant thing over here in the corner. It's really tiny. And if you look at that, compared to the other, to the planets in the solar system, you start to wonder, you know, what the heck is going on here? It really doesn't fit the pattern of what's going on in the solar system. It also doesn't fit the pattern of the orbits of the solar system. The planets are all in these very beautiful circular orbits in a single disk going around the sun. And Pluto, this was known very early on, Pluto is in a very crazy orbit. It kisses the orbit of Neptune in here, goes out further, elliptical, and if I had been able to turn this screen on its edge, you would see that Pluto is tilted by about 20 degrees. It makes no sense whatsoever as part of this system of planets. But in 1930, there really weren't any other options to call it. There was nothing else out there. There's an asteroid belt that's interior, but then there's Jupiter, Saturn, Uranus, Neptune, empty space, and then this little thing. It didn't make any sense to call it anything else. And so planet was the most natural thing that you could possibly call it. All right, so we're going to fast forward. Before we fast forward, I'm going to remind you that Clyde Tombaugh, even Clyde Tombaugh, if you read his writings about Pluto, he was a little bit unsure about this thing. In fact, he was not convinced that Pluto, even when he first discovered it, he wasn't convinced that it was the thing that was tugging Neptune. And the reason why he wasn't convinced is because he looked at it. It was so small. He thought, it's hard to imagine this thing being so dense to tug on Neptune. So he spent the next 10, 15 years surveying the entire sky, or at least as much of the sky as he could see. And this is how much he did. This is a map of the sky with here's the North Star would be up here, the Southern Cross would be down here, The ecliptic, along which all the planets go, is in through here. And he surveyed this whole yellow region in through there. A tremendous area of the sky that he surveyed night after night after night by taking these photographic plates on his telescope and developing them and looking at them by eye. Just an amazing job. He found many things in the survey, but he didn't find anything else, any other planets out there. And he was left to conclude that was it. Pluto really is this lonely oddball out at the edge of the solar system. And as far as anybody knew, it really was. That was it. It was the only thing out there, and a strange thing out there. All that changed in 1992, when the very first other object out beyond Neptune was discovered. And by today, there are something like 1,200 known objects in this region beyond Neptune. Here's the planet scan: Jupiter, Saturn, Uranus, Neptune. Each one of these little diamonds is an object in what is now called the Kuiper belt, in this region outside of Neptune. In fact, some of them you see are actually inside of Neptune, and even all the way in through here. These are objects that used to be out of the Kuiper belt and have gotten a little bit too close to Neptune at one point, got flung inward, just like when we send a spacecraft out and we gravitationally assist them outward. They've had a nice little gravitational assist inward. They've been flung inward to eventually become comets. It's one of the sources of the comets that we see that comes by the sun. So these 1,200 objects that are known today were all found the same way that Clyde Tombaugh found Pluto. You take a picture of the sky, come back an hour or two later, take another picture of the sky, find something that moves, and you know you're onto something out there. And Pluto, in fact, is this little blue one right here. And if you look, actually Pluto does a very nice job of defining both the inner and the outer part of the main region of the Kuiper belt. As soon as you see this about Pluto, and if what I can't show you is the orbits of all these little diamonds, because it would get a little bit too confusing, but if you looked at the orbits of all those diamond-shaped things, they would all look like Pluto. They're not all exactly the same, elliptical or tilted exactly the same way, but it's just a big mess. And you can see that Pluto very naturally fits amongst this mess, as opposed to fitting in the nice orderliness of the planets. Even back in the days when we were crazy enough to still be calling Pluto a planet, it was very clear that you had to say that Pluto was both a planet and part of this Kuiper belt. It would be crazy to say it's not part of this Kuiper belt. Crazy to say it's a planet too, but there are crazy people out there. So let's put all the rest of the Kuiper belt on here and talk about these early days of the Kuiper belt. This is sort of 2002-ish. You can see there's Pluto still there, and then there's all the other Kuiper belt objects that have been found. And the biggest ones are the ones that I can put on the screen. There's one that's about a third the size of Pluto that was known by about, this is about 8 years ago that I'm showing you. There's one that's about a quarter of the size. And the argument that was made then, this is again about 2002, the argument that's made then is that sure, Pluto is part of this Kuiper belt, but it's bigger than everything else in the Kuiper belt. It still has a special place amongst the Kuiper belt, so we don't have to do anything with it. We can leave it where it is. This is about where I came into the story, and I had looked at all these objects in the Kuiper belt, had thought about the Kuiper belt, and realized that one of the main reasons that we didn't know if there were any other larger objects like Pluto out in the Kuiper belt was not because astronomers had surveyed the whole sky and realized there was nothing else out there. It was because astronomers had done something that initially seems a little strange. Clyde Tombaugh looked at this much sky. And up to 2002, astronomers had looked at about this much sky. This seems a little funny, right? But I gave this talk to a second grade class once, and this second grader raised his hand and he said, well, how come astronomers are so stupid? And that's the panel that's next here in this room. So get that question answered. But in fact, astronomers aren't stupid. It's very obvious when you realize what's going on. Is that this was just at the time when CCD cameras were getting to be big in astronomy, and it's the same time that CCD cameras and digital cameras were getting to be big in everything. At this point, I am sure that there is nobody in this room that does not have a digital camera. Is there anybody who would claim to not have a digital camera in this entire room? Wow, so this is interesting. This is actually the first time that I've ever been able to give a talk and no one has claimed. Sometimes in the last couple of years people say, I don't have one, and then I ask them if they have a, so, do you have a cell phone that has one? Yes or no? No. Let's see, no cell phone, no camera. Well, we'll talk later. So here's the problem. The laptop, yeah, does the laptop have a camera?
I have a laptop.
It has a camera? Do you have a webcam? may win. I'll come up. You must have them. Everybody has it. People who don't even know they have cameras have cameras. Does it have a camera? Okay. Well, here's why you're bad people. Because every time you guys have gone out and bought a new camera, what happens? Well, if you're like me, so I buy a new camera about once a year, only because I lose my camera about once a year. When you do, you spend like $300 on your new camera, and every time you get a new camera, it has, I remember the first one that had like half of a megapixel, and I thought that was the coolest thing in the world, and now I haven't actually lost a camera in a couple of years. If I spent $300 on a camera, how many megapixels would I get these days? And what would I do with them all? Does anybody know? Okay, but astronomers at this point still had those tiny little cameras. The typical astronomical camera covered about as much sky as you can see. If you take your fingers, squish them together as hard as you can, and hold them out at arm's length. That's about how much sky these initial astronomical cameras covered. Now imagine trying to cover the whole sky by doing this. It would take you a very long time. Clyde Tombaugh, in contrast, when he wanted to cover big chunks of the sky, he was using the still primitive but fabulous technology of photographic plates. Photographic plate is literally a piece of glass with photographic emulsion painted on the back of it, and you can cut a pretty big piece of glass and slap it on the back of your telescope, and he would cover about this much sky once. So that was pretty good. But in 2002, we finally realized that the technology was getting better. Enough of you had bought cameras, not all of you, but enough of you had bought cameras that the technology was getting better, the prices were going down. We could finally, we put together this thing that at the time was the biggest astronomical CCD camera in the world. And in 2002, this was very impressive. Now it's, by next year you're going to have this in your pocket. It was 182 megapixels, all sort of held together with bubble gum and baling wire, and you had to kick it every once in a while to make it work. But it worked, and so we got that camera. We put it down at my favorite little telescope down at Palomar Observatory. Is not. I'm sure some of you have been down and seen the 200-inch telescope down at Palomar. This is the one you don't get to see on the tours, which is too bad because it's so much better. This is the 48-inch telescope. It's the one that back in the 1950s and then again in the 80s and 90s did the big Palomar sky surveys, the big photographic Palomar sky surveys. We ripped out all those photographic handling systems there, slapped onto this crummy little CCD that was the biggest in the world, and did one other thing that really made my life much better, which is put this thing. This thing is a microwave link that goes down to a site in the middle of the forest and then reflects over to San Diego Supercomputer Center, where then by internet up to my office in Pasadena. The fabulous thing about this for me is that from 2002 to 2009, when we were running this survey night after night after night after night, almost every single night, I think I went down to the telescope 3 times. And I never stayed awake because it was all done robotically. And I did things that normal people do during that time, like get married and have kids and stuff like that. So I like to think of this as the only reason that this project was really possible, because I don't think I could have done it otherwise. So what did we do? Well, all the astronomers up to 2002 had covered this much sky, and since from 2002 to 2009, we actually finally finished this part. We covered this much sky, which, yeah, try this again. They had covered this, we covered this. Oh, you guys are not impressed, are you? Oh yeah, well, we found cool things. Sorry? Yeah, well, so the Milky Way goes here. Yeah, I should point that out. Here's the Milky Way. We avoided it because the first time we didn't avoid it, we realized it's a complete waste of time. There's so many stars and everything else in the Milky Way that you're looking for these little Kuiper belt objects there. It just is junk. We also missed this little section of the sky, which is the far northern sky in January, and it was for 5 or 6 years in a row. We just got no clear nights in January, so we never. It's probably like the biggest Kuiper belt object in the world is heading right there. So it's going to really irritate me when somebody finds it. But most of the ones, by the time we got up this far off of the ecliptic, we weren't finding that many more, so we were willing to finally give up. So let me show you. I'm going to tell you a little bit about exactly what we do, show you some of the stuff that we found, and then talk about some of the discoveries. So what really happens? Well, the telescope gets a list of places in the sky to go look each night, and then it takes 3 pictures of the sky. It takes 3 pictures about an hour and a half apart. And in the morning, all those pictures are transmitted back to Pasadena. A single image. So I told you before that the astronomers before could cover about this much sky. And Clyde Tombaugh covered about this much sky. We cover about this much sky all at once. It's not bad. It's still not as good as if you were Clyde Tombaugh, but you can imagine if you've been doing this for 7 years like we have, that you could actually cover a significant chunk of the sky and see what you see. So we get these images back in Pasadena. The computer does most of the processing. Again, this is, I am continually, every time I think about this very hard, I'm continually in awe of Clyde Tombaugh having found Pluto. He stayed up all night taking pictures with these photographic plates that he then had to develop, that he then had to look at in the day, and then he then had to go observe the next night again. It's amazing that he actually lived for more than about 5 years trying to do this, much less actually found things. We do this all mostly by computer. The computer takes the images, sends them down, does the analysis, looking for little things that move, and all that I do at the end, other than write all the software that makes it happen, is look at those last little images that the computer has picked out and decide if they're real or not real. The computer I have carefully tuned to be not very good, because I would much rather have the computer show me a lot of junk and get to pick it out myself than to have the computer decide, oh no, that's not real, I'm going to throw it out, and then find it much later. Actually, that happened, but we'll talk about that later. So, what does something look like? Well, when the computer gives me a little postage stamp in the morning of an area where it thinks it's found something, it'll look something like this. Here is 3 images in a row, and here's stars that are all in the same place over the course of those 3 hours, and right in the middle, you can see this little thing moving, 1, 2, 3, 1, 2, 3. You can immediately tell a lot of things about an object that you find by looking at just 2 things, by looking at how fast it moves and how bright it is. How fast it moves is a direct function of how far away it is. Things that are really close to us move very quickly. It's all just, it's parallax, just like you're looking out the window as the car going by. So the mailboxes are moving by really quickly, the mountains are barely moving. Same thing here. The asteroids, the meteorites, the airplanes that fly overhead all the time in San Diego are moving very quickly. The things that are near Jupiter are moving still pretty fast, and finally the things that are out in the Kuiper belt are moving very slowly. And this is one of those that's out in the Kuiper belt. Where is it? There it is. This is one of these that's out in the Kuiper belt. It's moving at a typical Kuiper belt speed. So I can tell you just from looking at that picture right there that it's sort of in the middle of that region between the orbit of the inner and outer edge of Pluto. It's sort of there. I can also tell, based on how bright it is, about how big it is. I can't tell exactly how big it is, and we'll talk about that later too. But I can tell about how bright it is. This one's pretty faint compared to most of the things we see. This one's probably, I'm going to guess, about 21st magnitude. And that, something that's 21st magnitude at about the distance of Pluto and a little further away, it's not a particularly big object. It's probably, this one's probably 200-300 kilometers across, 10-15% of the size of Pluto. So it's, it's probably in the top 100 of the Kuiper belt objects found. But it's a typical one that we found of the hundreds of these things that we found out there. I'm just going to flip through a few of these for you just to give you the feel for what it's like. Here's one. It's a little brighter. So it's moving about the same speed. Let's go with the speed first. It's moving at about the same speed, which means it's about the same distance, and it's brighter. Brighter means it's bigger. This one is actually, turns out to be about a third the size of Pluto. Here's another one. This one is going a little bit more slowly. I don't know if you can tell it's moving a little more slowly, but it moves a little less distance here. Moves a little bit more slowly, and it's about as bright as the last one. That's kind of interesting, because a little bit more slowly means that it is further away, but it's as bright. So if it's further away and as bright, it must be a good bit bigger, because all of this is just reflected sunlight from the sun. So you've got to be bigger to be a little bit brighter. So this one is getting to be almost half the size of Pluto. This is a pretty big, substantial object. This is maybe in the top. Am I there? Yes. This is maybe in the top 10 of the Kuiper belt objects that we know out there.
What's the fast-moving one?
The fast-moving one I was about to say. If you look very carefully, here's another one. One, two, three. Any guesses? It's an asteroid. So as I said, the closer you are, the faster you move. That's about the typical speed of an asteroid out there. It's very convenient for us because they very easily sort themselves out. So we see probably tens of thousands of asteroids in these data. And if we had to track down every single one of those asteroids and ask what it was, we would be spending a lot of time. But we just ignore all those ones out through there and only look at the interesting stuff. I'll feel really bad, I admit, when one of the ones we ignored ends up hitting us, but I'll get over it. Okay, so let me show you one more, and this one more, I will tell you, this is one more that I found on the morning of January 5th, 2005, and as soon as I flipped that onto my screen, I did three things. First thing I did is went and double checked, because every time you find something exciting anywhere in science, chances are you did something wrong. And so, and you know, you do it all the time. I figured this can't be real, I'm gonna go check it out again. And the second thing I did is said, no, really, this is stupid, I couldn't have done this, and I checked it out. And the third thing I did is almost fell out of my chair. And I almost fell out of my chair, why? It's slow, so it's really, really far away. Not only, so it's so far away that it's beyond that outer edge of the Kuiper belt by about a factor of 2. And it's the brightest thing we'd ever seen. So if it was the brightest thing we'd ever seen, it'd be really exciting. If it was the furthest thing we'd ever seen, it'd be really exciting. If it's the brightest and the furthest of that we've ever seen, the technical term is very, 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 very exciting. Because I think that if you cube the excitings or something. This thing was, it was clear from the first moment that this thing was the biggest thing we'd ever found, the most distant thing we'd ever found. And it took me about 15 seconds to get out my pencil and calculate how big it should be if we were going to see it this bright, this far away. And it was very obvious to me that this thing was at least as big as Pluto and likely much, much bigger than Pluto. This is the point, though, where I have to admit that when all these times when I've been telling you about how big things are, I've been cheating a little bit. And the reason I've been cheating a little bit is because we don't know instantly how big things are when we see them out there. And the reason is because, again, as I said, they're reflected sunlight. And all you see is how much sunlight is being reflected from them. You don't really intrinsically see how big they are. And you can imagine that something that is huge but covered in dirt will reflect a lot of light back to you. And something that's kind of small and covered in snow will also reflect a lot of light back to you. And those two things look exactly the same to me. What I knew, though, is even if it was small and covered in snow, it was still bigger than Pluto. What I didn't know is what it was actually covered in and how big it really was. And I remember sending email to the two guys who I worked with on this project, Chad Trujillo out at the Gemini Observatory and David Rabinowitz at Yale, and I sent an email telling them that we had just found this thing and giving them the table of how big it would be if it had these different things on the surface, and the one at the bottom was if it was covered in dirt, basically, then it was the size of Mercury, which was going to be very exciting. And we didn't know, and so we were interested to go see how big this thing was. Before we could see how big the thing was, though, we had to figure out where it was, what kind of orbit it had, what it was doing around the sun. And usually, for these things, when you discover them, it takes a couple of years to figure out what kind of orbit they have. You can imagine how irritating I would find that if I had to wait a couple of years to figure out what kind of orbit it had around the sun. But the nice thing is, as an astronomer, you can do one other thing, which is you can go backwards in time. And the way you go backwards in time in this particular way is you go back to old data that people took and saved. And a lot of people take pictures of the sky, there's a lot of them you can just find online, like the Palomar Sky Surveys, other stuff you can find in old archives. A lot of people take pictures of the sky, and you take your very short amount of data that you have right there, and you predict where it should have been a year ago in the past. And you go look at pictures from a year ago, and sure enough, in pictures from a year ago, there's a star right where you think it should be, and if you go look at pictures of 2 or 3 or 4 years ago, that star wasn't there. It doesn't tell you for sure that it was really the star, that's really your object. You know, it could be some gamma ray burst or something horrible like that going off in the sky, but it was interesting that it could be your object. Then you take that one and you go back another year and say, well, if that was really real, this one should be here. And sure enough, there's something there, and if there's one here, it should be here. And we eventually found this all the way back. The very earliest image we found of this object was from 1954. And it was from 1954 from the Palomar Sky Survey, taken by the same telescope, which I think is just kind of a cute story. So what kind of orbit does it have? Well, we were really wanted it to have a big circular orbit like you know, a real planet should. So I'll admit we were a little bit disappointed. I've already said all this stuff. That's where it is. We were a little disappointed to see that the orbit was actually a very typical looking Kuiper belt orbit. It was there's Pluto again on its very crazy elongated orbit, and this one goes very far away from the planets, but it comes back in. A lot of the other objects in the Kuiper belt, although most of them spend most of their time in that region around Pluto, a lot of them have been sort of flung out and come back in again. So this one did not look like it had sort of a planetary orbit. It looked very much like part of the Kuiper belt. And what's more is if you turn this one on its side, you can see that here's Pluto tilted by its crazy 20 degrees. This thing is tilted by 45 degrees to the planets in the solar system. We still actually don't understand that one. Usually when something funny is going on in the outer part of the solar system, we blame Neptune. So I blame Neptune. But I don't know what Neptune did. We're still trying to figure out what happened in through there. Okay, so we got the orbit. As soon as we got the orbit, we were starting to be a little suspicious that this thing might not be as big as Mercury and on a sort of planetary orbit. But we needed to find a way to really get the size of the object. Astronomers have been now for years have come up with these very clever ways of figuring out the size of objects when you can't actually see them and see how big they are, and you measure the amount of heat coming from it, and you do all these other calculations, and you come up with the size. But we came up with what we thought we were very clever to come up with this new idea. We thought we would take a picture of it and see how big it looked. No. So the only reason we could possibly do this is if it was pretty big. Everything else in the outer solar system you can't do this with. And even this one you couldn't do it with except for one telescope that works particularly well. The Hubble Space Telescope is the only one we knew if we could that it might just barely be able to resolve this thing. So we were pretty excited about this one. When the data came down, it came down onto the ground like in the middle of the night, and I remember driving into my office in Pasadena to download it onto my computer, quickly displayed it on the screen, and it looked something like this. And I said, oh, did we look at the wrong thing? It's that's not very exciting. In case you guys were wondering if this was exciting or not, this was not very exciting. This is likely the best image you'll ever see of this thing in your lives. We won't really have any better ways of doing it. And it's not very exciting. Not only is it not very exciting, it's even less exciting than it looks, because most of what you're seeing is even due to distortions of the Hubble Space Telescope, which, as good as it is, still has some inherent limitations. The actual object, oh, that's not good.
That's
Okay, let's see. That's why I was kind of doing that. Okay, there we go. The actual object itself is only actually about that big. And the only way we could tell it was by carefully comparing back and forth between stars and blah, blah, blah. That red circle is 2,400 kilometers across, or in the only units that anybody cares about, 5% bigger than Pluto with an uncertainty of about 4.5% or so. Okay, so let's put it on the plot. In the meantime, we found a bunch of other things. There's still Pluto on there. There's a lot of the other bigger ones in through there too, including some kind of strange shaped ones that we found. So we had been filling in this plot a lot by finding all these bigger objects. So we found something that was 3/4 the size of Pluto. We found some that were 1/2 and 2/3. Really had filled in a lot on this plot. And now let's put in this new one. You guys ready? Looks like this. Whoa. Wait, here was the solar system before. Here's the solar system after. Before? After. So, I have very bad news for those of you who came all the way here to hear about this, and for me who spends my whole life doing this. This doesn't matter at all. This makes zero difference to the solar system. Whether this object was there or not there makes no difference whatsoever. It is, in the grand scheme of things, a fairly insignificant chunk of real estate in our sky. And I think you can see that pretty well just by seeing what it's like when you get rid of it and you put it back. So this means nothing. This changes nothing. This discovery changes nothing in astronomy. The problem is, it changes everything. I'm sure some of you were at the panel discussion yesterday, and I said this before. It changes one very important thing, which is, for a long time this debate had been about, is Pluto a planet or not? Astronomers tend to be very conservative. Nobody in astronomy wanted to get rid of Pluto, well, except for me, because they knew it would just be a hassle. and they would have to deal with, you know, irate people sitting next to them on airplanes and things like that. So nobody wanted to get rid of them, for the most part. But when you suddenly find something that's bigger than Pluto, you have to actually answer the one question, which is, what is that thing? Who cares what Pluto is for a minute? What's that? And you have to answer that question. You are suddenly forced to answer that question. And of course, everybody knows the story of how that question was answered. The august astronomers of the IAU bickered and fought and made for a very generally hilarious time for those of us who were watching overseas and reading the newspapers, and eventually came down on the side of Pluto's not a planet. There are 8 planets, and then there's a class of dwarf planets. And it was, of course, big and huge and controversial. And a lot of people, even scientists at the time, were not very happy about it. I think most of the scientists are pretty happy about it too these days. And most people have decided that they don't really care that much anymore. In fact, if you run into an astronomer anywhere and you ask them about Pluto and a planet, the first thing they'll always say is, you know, none of this matters. It does not matter at all. It's just a question of semantics, and it doesn't matter what we call Pluto. And then they'll spend the next 3 hours telling you why their definition is right and everyone else is wrong. And so I hope you guys have 3 hours, because this is where I now tell you why I'm right and everybody else is right. But I'll do it in less than 3 hours, I hope. So here's what I would say if you ran into me on an airplane and you said, you know, so what's up with Pluto? I wouldn't say it doesn't matter. I would say it actually matters critically, what we call Pluto and what we call these other things in the solar system. It doesn't matter in a scientific sense, because scientifically, it's all just a question of classification. Scientists always classify things. They always approach any new set of phenomena as something to first classify, and classification as the first step towards understanding. And so, any set of phenomena, any birds or rocks or planets or stars or anything, you can classify in so many different ways. You could classify birds that live in the water, birds that are red, birds that have big orange beaks. You can classify any of these things, and they're all perfectly valid classifications. Some of them are more useful than others, depending on what you're studying, but they're all just ways of classifying things. So there are astronomers who have really wanted to classify planets as everything that's round is a planet, and everything that's not round is not a planet, as opposed to the big 8 things here are planets, and everything else is not planets. I believe that simply by showing you this picture, you almost get the entire argument, and I really don't even have to make it. My argument is simply that it is very difficult as a rational being to look at this picture of the sizes of the objects in the solar system and to say, okay, I'm going to make a category, and I'm going to put these things in one category, plus that's series. That goes into that category, and these 1, 2, 3, 4, these go into that category, and the rest of them are all in a different category. It really is very difficult to think of that as the first classification scheme you would do for these objects. It's a perfectly good one. Round things kind of matter. They might be geologically interesting. And if you're a geologist, you might even care about that sort of thing. But as the single most profound description of the solar system, I think what you need to say is that the solar system consists of the sun, somewhere off the screen, 4 terrestrial planets that are grouped here, 4 giant planets grouped here, a population in the middle here, and a population on the outer end. And if that's your view of the solar system, and that the 8 planets are separate from those 2 populations, you have the simplest and most profound view of what the solar system is. This is the solar system that we as scientists try to understand. We try to understand why there are terrestrial planets in the interior, why there are giant planets on the outside, why are these places where you might have thought there should be planets and there aren't, there are these populations instead. If your view is simply that, Pluto's a planet and everything else sort of round is a planet, then all you have done is said, I know why things are round. Things are round because of gravity, and that's just the end of my story about the planets. I like this one much better as the much more profound view of the solar system. It's still just classification, so there's no reason to say this classification is better than this one. But the problem is that we talked about at the panel yesterday again, there's this magical word, planet. Most of the public will never learn anything about the solar system except that there are planets and there are a certain number. And I want them to have the best picture of what the solar system is. The best picture they could have, if they're not going to learn anything else, the best picture they could have is that there are 8 planets. And that's essentially the solar system. There are other things, and these are very interesting, important parts of the solar system, but if they only know that there are 8 planets, that's at least a start. If they think that this one should be a planet too, and they don't know that this population is out there, I feel like they've really gotten the wrong picture. And that astronomers arguing about Pluto being a planet, and that it should be just sort of out of sentimental reasons, have really tried hard to give this wrong picture of what the solar system is, which I find sort of deeply offensive to my educational sense. So this ends the editorial portion of the talk. But I actually really, as you might be able to tell by now, I actually think it really matters. It is not just a question of semantics. It's a question of what do people know about the solar system. And I think this is the right thing for them to know. And I encourage you all to go and convert as many people as possible. Okay, so after the editorial portion, the main reason for discovering these things, of course, is not just to get astronomers to argue amongst themselves, although that's an added bonus. The main reason is to get to do a little bit of science. And there's some very cool science that you get to do when you find these things. As soon as we found this one, I have to, the one quick aside that I'll do is this, I'm going to be calling it this and this one. And so most of you, of course, know that this now has the name. Once it was decided what it was, dwarf planet, it finally was allowed to get a name. So its name is Eris, E-R-I-S, and Eris, of course, is the Greek goddess of discord and strife, which was just sitting there waiting for us. So it was like one of the only major gods or goddesses in Greek or Roman mythology that hadn't been used for a planet or an asteroid or a Kuiper belt object. They're just sitting there, Makes you almost believe in astrology, I think. Or maybe not. So after the discovery of Eris, we got basically every telescope that we could get our greasy fingers on. We went and looked at them, and one of the most exciting ones was very early on. We got a chance to go to the Keck telescopes in Hawaii. My favorite little telescopes are big telescopes. There's Maui in the background, and the Keck telescopes. This was brand new at the time. I'm sure a lot of you have heard of this by now. The Keck telescopes had this brand new laser guide star adaptive optic system, which is just about the coolest thing in the world, because the way these things work is you take a laser at your telescope, you shoot the laser up in the sky, and at the very top of the sky, there's a thin layer of debris left over from meteorites that are coming into the Earth's atmosphere. And from that thin layer of debris, the laser reflects and comes back down to you, and you look at the laser in your telescope. Well, of course, the laser, now it's traveling through the atmosphere, and so the laser's all wobbly and doing crazy things. And then you have a little mirror at the bottom of it that you can adjust a couple hundred times a second to make that laser that's going all wobbly to suddenly go into a little point like that. So you've now just spent several tens of millions of dollars to take a picture of a laser and make it not wobbly, which is all exciting, but the nice thing is if you know what you're doing, you make sure to point that laser right at something that you really care about. And the same thing happens, that your star that you're looking at, initially waving around because of the Earth's atmosphere, you turn on the laser and the system, and you can watch it. It happens in real time. It just goes like this, and it suddenly goes to this little spot in the sky. But sometimes it doesn't. Sometimes it goes next to it. And that little next to it is this. This is the moon of Eris that we found in this system. This is the moon of Eris, of course. You get to name all these things. So the name of the moon is Dysnomia. Dysnomia is a daughter of Eris and the demon spirit of lawlessness. Eris didn't have very nice children, but there's a good story behind this one too. So the moon is nice. One of the nice things about the moon, as soon as we found the moon, people said, "Oh, it's got a moon, so it must mean it's a planet, right?" And I had to point out that no, something like a third of the objects in the Kuiper belt actually have moons around them. So having a moon doesn't make you a planet. And I pointed out that Mercury and Venus don't have moons around them, and they're still planets for now. So it's not that, but what it is, of course, is you get to do some real physics. If you have a moon around you, you can track the orbit of that moon and go in a circle around you and figure out exactly how much this thing weighs. How much this thing weighs mattered to me a lot at this point, because you might remember that it was sort of 5% with some uncertainty bigger than Pluto, and you can do very precisely with doing the orbit of this. So we got the orbit from both the Keck telescope and from the Hubble Space Telescope. Very nice image from that. And we got the orbit by looking at it a bunch of different times. And as we were finally doing that final calculation, one of my graduate students made a bet with me, because she was convinced that it was going to weigh less than Pluto. And she had no real reason to be convinced of that, except that she thought it'd be really funny if I had to go announce that in public. It's like, oh, well. And so she was really looking forward to me being embarrassed. And if she won, I was going to have to owe her a case of champagne. And if I won, she was going to have to stick around in grad school for an extra year. So it turns out it's 25% more massive than Pluto with an uncertainty of only about 1%. So it really is a good bit more massive. And she did really nice work that extra year in grad school. So it was win-win, I think. So there are a lot more things that I would love to have the time to talk about. Most of the time you only get to hear about the one big object that was bigger than Pluto that was found, but there are a lot of other very fascinating objects out there that we found, including perhaps my favorite one, Hubble, which is shaped like a big egg and rotates every 4 hours because it got smacked early on in the solar system and debris went flying everywhere, and you can track down the debris. It's got 2 moons around it. Crazy system that we're still studying in gory detail. There's Maki, which is actually a little bit of a Pluto twin. It has an atmosphere and a surface just like Pluto. We're finding these things. We're finding that Pluto is no longer this oddball at the edge of the solar system, but it really is sort of the prototype of this new large class of icy methane dwarf planets. They're a very fascinating set to consider. I will tell you in closing about one more object, because it remains still, I think, the most intriguing object that we found, and also points to what we might be finding in the future. This one was one of the early ones we found. This was back in 2003. And in 2003, we found this object that was, here's the number of objects that were known in 2003, and we found this object that was way over there. And now, if you're paying close attention, of course, you remember that that's sort of the same distance that Eris was found away. But at the time we hadn't found Eris, we hadn't found anything at that time out at those distances. So we found this thing, we were so excited. We were convinced that this has to be a planet, it has to be in a circular orbit, this was going to be great. We did that same trick, finding images back and back and back and back to figure out what the orbit is. And the orbit turns out, we have the 2 big questions, where it's going to be circular, like a planet would be, or is it going to come in like a comet would be, or a Kuiper belt object would do? And the answer is no, it actually does that. This is Sedna. Sedna is the Inuit goddess of the sea, and she lives in an ice cave under the Arctic Ocean, and so it seemed like an appropriate name for something that's so far away and so cold, probably the coldest thing that we know of in the solar system. We still don't know how this thing got on its very crazy orbit. It's actually a very difficult thing to do. You can't do it with the planets that we have in the solar system. Something else intruded. And there are a lot of theories as to what was the intruder. Was it a star that came by early, a cluster of stars, another planet? Who knows what was out there? So that's scientifically that's interesting. But the other interesting part of the story is that Sedna spends so much of its time so far away that we would almost never detect it. It takes 12,000 years to go around the sun, and we could see it during 200 of those 12,000 years. So if you do the math, that's 1/60th of its orbit we had a chance of seeing it. So either we were extremely lucky to find it, or, the way astronomers tend to think, if you had a 1 in 60 chance of finding it, probably that means there are about 60 of them out there, and you found the one that happened to be close. And maybe we got a little lucky, maybe there are 30, and we got lucky. Maybe there are 90, and we got a little bit unlucky that there's only one. But there must be something like 60 of these objects the size of Sedna out there. Sedna is about 3/4 the size of Pluto. This region out through here is huge compared to the Kuiper belt. There are not that many objects 3/4 the size of Pluto in the Kuiper belt. In this region there are at least 60. If you extrapolate sizes of objects, which is always a dangerous thing to do when you have one object to start with, but if there's 60 objects, but I'm going to do it anyway. So if there's 60 objects 3/4 the size of Pluto, and you have sort of typical sizes that you have in the solar system, then you would end up with probably 30 objects the size of Pluto. That's a lot of objects the size of Pluto. You would end up with maybe 10 objects twice the size of Pluto, and you might go with 1 or 2 that are 2 or 3 or 4 times the size of Pluto. We're getting to be the sizes of Mercury, Mars, even Earth. I think it's very likely that somewhere in these regions out there, you're going to have something that is Mars-sized, Earth-sized, way out there in the outer part of the solar system. We've spent the last couple of years looking hard to see if we could find some that were close. And we didn't. The problem is they spend most of their time in those very distant regions, so they're going to be hard to see. As I said yesterday in the panel discussion, if you heard it, is that if we find this thing that's out there, that's the size of the Earth, the size of Mars in this outer region, by the currently accepted definitions of planets and the conceptual definition of planets, it is still considered a dwarf planet. It is not a planet. I suspect that this will open the can of worms once again, and I will look ridiculous as the person who will argue, and I will absolutely argue, that it should not be considered a planet. It should still be called a dwarf planet, even if it's bigger than Earth. And I predict I will lose that argument. And that's okay. So I would say stay tuned. The place that we're most likely to find this thing, now we've looked all up in here, assuming it's not right there, which would really, really irritate me. The place most likely to find this thing is now the southern hemisphere. The southern hemisphere is unexplored territory. It's ready to go. So we're starting a survey right now from Australia. You can tell it's Australia because it's got sort of funny-looking trees. And the sky is always cloudy. So the survey is starting now. I would say within the next year or two, if there are big things down there, which we don't know if there will be or not, then you'll be starting to hear about them. So stay tuned, and I hope to be able to come back sometime and tell you what the view looks like, not from Eris, the largest dwarf planet, but maybe from something even farther out, the largest planet out there, maybe the new 9th planet. And just the shameless promotion part, if you want to follow along as we go, you can read along on the blog, which sometimes is more active than others. But if you really want to know, where I am day to day, you can always find me on Twitter. And of course, the book is coming out on December 7th, and you can pre-order on Amazon now. It's already in the top 2 million on Amazon. I'm very excited about this. So anyway, thanks for sticking out to the end of this, and I'd be happy to answer a few more questions now. And if you don't get your question in, I'm somewhere over here for the next session for question and answer too.
We do have time for a few questions. I'll let you go right.
Okay, I'm going to always go to the end, but the back, which no one ever does.
About 7 slides back, the picture of Eris with dysnomia around it, there was a slight kind of plume, a bright plume. Is that because the planet's not circular? Is it because...
No, it's actually a background star. So we were tracking it for a few hours, and so it moved across the star in front of it. But yeah, you're absolutely right.
Were you able to get a diameter in that star?
No, because the adaptive optics at Keck is not nearly as stable as... It didn't occult. Oh yes, I see your question. No, it just came close. It didn't occult. Wait behind you.
As a student who spends a small or large fortune on textbooks, I just want to make sure this isn't some giant conspiracy, so I have to buy more editions of my astronomy.
This is not required to be part of the giant conspiracy because textbooks already are a giant conspiracy, and so they would make new editions no matter what. So, but they do give me kickbacks, so that's okay.
When comets come in from a great distance, they always talk about something perturbed the Oort cloud to get that comet in the inner solar system. They used to talk about passing stars. It seems far-fetched. But could there be something Earth-sized, Mars mass?
Let me answer the question, which is, it's not far-fetched. It really is passing stars. They don't have to get very close. If you have something that is really, really far away from the sun, just incredibly loosely bound, it doesn't take much to give you a kick to come inward. There could be large objects out there that are doing it too, but they are not large. Stars are so massive, they have such a huge region of influence. So it really is passing stars and galactic tides. I have the same feeling you. It just seems so unlikely, yet it's really true. Okay.
Mercury's starting to look a little small.
Yeah, well, I've got plans for Mercury.
That's the sequel.
That's the sequel. There's this spacecraft that's visiting Mercury. Most people don't know it's packed full of nuclear explosives. Okay.
Since Pluto turned out to be smaller than expected, what was actually perturbing Neptune that led Flight Combo to look in that?
Yeah, so I should have mentioned this part, and I just slipped my mind to say it. The question is okay, so Pluto was not perturbing Neptune, so what was perturbing Neptune? The answer was nothing. It turned out to be bad data. There was a very careful analysis done in the early 1990s that went back and looked at all the data and said, look, there really is no evidence when you do the job right. There's no evidence whatsoever of any perturbers out there. Doesn't mean there's not something very far away out there, but it means that there was no need for that perturber. And so the Planet X that everyone was looking for was simply not there.
So it's pure serendipity, but where's the Oort cloud compared to the Kuiper belt?
Yeah, if I had, on that picture that I showed you of Sedna, where you saw the outer edge of Sedna, take that picture and then go out to the Great America parking lot. And then that's about the right distance. You're about right.
There are some guys out there that built a probe named New Horizon to send it to a planet named Pluto.
Yeah, they're mad.
And yeah, do you ever meet one of these engineers that you killed his planets that they sent a probe to?
Yeah, so the question is, do I ever meet the engineers who built the probe to planet Pluto, which now turns out to be dwarf planet Pluto? I actually don't think I've met the engineers, but I meet the astronomers who are involved with it. And they're kind of bad, which is kind of fun.
So given that we didn't expect to find anything between the Kuiper belt and the Oort cloud, and then there was Sedna, in the realm of wild speculation, could you suggest what might be in between those? Are there more possible?
I'm a big fan of wild speculation. In fact, in the paper where we announced the existence of Sedna, we went down that road of wild speculation and suggested that really what you're seeing is the inner part of the Oort cloud. The Sedna, the Oort cloud as we know it, that thing that's being perturbed by stars, has to be really far away or it won't be perturbed by stars. But there are things that could be, that it still could be a continuum all the way out to there. I think the most likely explanation is that continuum was put in place at the birth of the sun by a cluster that the sun itself formed in, and it put all those things, perturbed and put them all around there. Those cluster of stars then disappear, and we're left with essentially a fossil record of the birth of the sun. So I think that this discovery is one of the most exciting scientific discoveries in the outer solar system. Sedna. Eris is great, but I think Sedna is where the real science is. If we can find more of these things, I think we'll be able to read this fossil record and really tell you what the conditions were when the sun was born. It's extraordinarily hard. We discovered it in 2003, and it's been my top priority since then to find another one, and I have not found a single one. It's not for lack of telescopes or anything else. We've been trying really hard.
Mike, I'm going to ask one final question as moderator, because I really enjoy your thinking about the names. So could you tell the audience a little bit about how these unusual names like Makemake came about, and what your ideas are about further naming?
Yeah, so the names that the discoverer gets the privilege of naming, which is fun, and I take it very seriously because these things are going to stick with these names for forever, and so I try very hard to have some reason for what the name is. So the very first big one we found was Quarwar, and Quarwar is. We didn't know enough about Quarwar to have any sort of tie-in to the body itself, but what we did know is that this was the first large object found. We were sitting in my office in Pasadena at the time, and most of the objects in the Kuiper belt still were being named for Greek and Roman gods, and so we thought, okay, we gotta get away from that. So we named it for the local Native American tribe, the Tongva, or the Gabrielino Indians. Are the ones who, the Mission Indians from Los Angeles Basin. And we wanted to name something after them. We found this name Quarwar somewhere. So we called up, well, first we had to figure out how to find them. And it turns out you go to www.tongva.com. It's true. And they have a phone number, and you pick up the phone and you call, and the chief answers. And it's also really true. The chief answers, and we say, we're astronomers at Caltech, and we found this thing out in this outer pond. We want to name it after one of your creation gods. And he's like, sure. Why don't you talk to this guy? So he sends us to their chief historian and tribal dancer, who's a great guy. And so we sat and talked to him for a long time about what the appropriate names were, and we came up with Quarwar together. And Quarwar, of course, so they now have a tribal dance in honor of the Kuiper belt object, Quarwar. They're very excited about it. And Quarwar, just in the last year or so, we discovered a moon to Quarwar. And so I called up the tribe and said, you guys, why don't you guys name the moon? So the moon's name is, so Quarwar is their creation force who sang and danced the world into existence. and his son was Weywuut. That's the name of the moon. So all of these have a little story to them that we take it very seriously. A lot of astronomers think it's just a big waste of time and they don't care. And I think it's both important and fun. It's important because people like the names. People think about the objects more if they have interesting names. You know, when Sedna was 2003 VB12, nobody really cared. When Sedna was Sedna, I got these pictures from school kids about the object Sedna. It's a big difference.
Can you spell it, Quasar?
Quasar is quasar with an O instead of an S.
All right. What I'd like to suggest is that some of you may know that recently Dr. Brown was elected to the California Academy of Sciences. And part of the reason was not just for his exceptional research, but also for his interest in public education. And I think he did a wonderful demonstration of that today. So thank you very much for an excellent job.
Thank you.